All right, as we know, the moon is engulfed by a plasma environment that comes from the solar wind and solar radiation on the lunar surface. And this plasma environment can charge any objects on the lunar surface, potentially causing electrostatic discharge hazard. And we also know moon is covered by a layer of fine dust, and this dust particles can be charged and even lofted in the lunar plasma and the electric field environment. It just doesn't work well. It's probably my problem. So this has been a long-standing problem, and that was first indicated from several Apollo observations. So here shows two examples. On the left, that's the lunar horizon glow. That's believed those dust particles are like 10 microns in diameter, lofted to a height of 30 centimeters. And on the right, it shows these high altitude streamers that are thought to be nanometer-sized dust particles, lofted to a height of tens of kilometers. So if this were proven to be true, those lofty dust particles can pose risks to exploration systems and activities as well. So for sure, we need to understand the lunar surface plasma environment to mitigate those hazards. And the LUNAR probe is still an optimal instrument to measure thermal plasmas, including their density, temperature, electric fields, and spacecraft charging. And also, it's relatively simple to build. But there still improvements need to be done for lunar surface plasma environment. So here are two examples. One is above the lunar surface, the plasma is not uniform. It's not homogeneous. It's actually a non-neutral sheath region with a potential gradient. And also the probes are subject to a self-emit photoelectrons on the lunar surface, which may contaminate your measurements of the true ambient plasma environment. So traditionally we use single sensor probes, which has limitations for those kind of measurements. So here we introduce our double hemispherical probe, which was first developed to improve space plasma measurements in broad scenarios, which is not necessarily for lunar surface plasma measurements. And on the left, it shows a diagram showing there are two hemispheres insulated from each other back to back. And you have two wires running through to them, so you can sweep the bias on both hemispheres at the same time. So you will get two current voltage curves. So the current voltage curves will tell you electron density, temperature, and the plasma potential. I will show you the curves in a later slide. And the differences between the two IV curves will determine any anisotropic conditions, including the two I just mentioned for the lunar surface environment. One is probe in the plasma sheath. One is a probe surface self-emission. And the traditional single sensor probes can tell you those information. So this is case one, DHP double hemispherical probe in plasma sheaths. And so you can see here on the top panel, that shows this is a test we done in the laboratory. So it's a potential as a function of distance from the surface. And you see this here, that's a slope, that's a potential gradient, which is the sheath region. And when you go out, the potential flats out, that's in the bulk plasma. And at the bottom panel is showing the current voltage curves. And of the two hemispheres, the first one showing when the probe sitting in the bulk plasma, the two dashed lines That's the current of two hemispheres, and they are virtually identical. So they don't see any difference. And when the probe moves into the sheath region, and you see these two dashed lines, they start to deviate. And when the probe moves into deeper sheaths, and they deviate more, and in which the electric field is stronger. So there's a correlation between electric field and how much of the deviation between the two hemispheres. And on the right, it shows the IV curves of the two hemispheres. You will see I will call the IV curves are actually stretched over the probe bias region. So that gives you hotter temperature and higher plasma potential, which mislead your probe measurements. So in the lab, we established empirical relations of the plasma potential, electron temperature, density, and electric field as a function of the current ratio of these two IV curves. And then we can back out the true values of them. And here, just give you an example of the TE measured versus TE true, the function of this current ratio for you to back out the true value. The second case is the probe self-emitting of either photoelectrons or secondary electrons. So on the lunar surface, most dominated by photoelectron emission. But here we tested in the lab, we did for a secondary electron emission case. So we have on the top, this diagram showing one hemisphere facing the beam electrons will emit secondary electrons.
3 minutes, Xu.
All right, thanks. And the other half facing away from the beam electron will not emit. And the bottom shows the IV curves of the two hemispheres, and the blue dashed line, that's the current of hemisphere facing away, so it doesn't emit. But you look at the red dashed line, that's the hemisphere facing the beam electrons. And on the negative potential, negative probe bias side, it shows higher current. And that current is actually caused by the secondary electron emission from the probe. So if you analyze the differences between the two IV curves, you can characterize the secondary electron properties, which can be then removed from data analysis for the ambient plasma properties. Whoops. All right, this is our engineer model development. On the left is CAD showing a CAD view, and it has top and bottom hemispheres. And then we have preamp board embedded, and the stub, which is electrically isolated from the both hemispheres and biased at the same potential to them to minimize its electrostatic effect on the probe measurements. And then we have a guard, which is also electrically isolated from the stub and biased more positive to prevent photoelectrons emitted from spacecraft from getting onto the hemispheres. On the right, it shows our physical model. It's a 5 centimeter in diameter, and it has gone through vibration and thermal TVAC testing. So we're at TR6. This development was through NASA's Picasso program. And for lunar surface plasma measurements, here are a couple of concepts. We can work with the DHP for sheath measurements. Come on. For sheath measurement, we need to have two hemispheres positioned to be parallel to the surface. And the IV differences between the upper and lower hemispheres will tell you the positional gradient, and when you can back out the true plasma measurements. To calibrate a probe self-emission, you will orient the probe one hemisphere facing the sun and another staying in the shadow So the one emits photoelectron, one doesn't emit, and that difference will characterize the photoelectron properties from probe itself. So you can only just calibrate once, and then you can do the rest of the mission.
That's about time. Try to wrap
Right.
up.
So I just be short. In conclusion, we're ready to fly it. So